Okay, so this is part two of the working with Candle and Rust series. Um, so the last, you can say part or last episode or however you want to put this, um, we went in part one of the series, we went through input embeddings. We basically talked about a couple of things over there. So let me see if I can pull those pieces up. So we talked about what an input embedding is. We said you pretty much take something like an English sentence like your cat is a lovely cat, and you sort of break them up into tokens. You could have tokens that are not just word, that is word level tokens, but you can also have tokens that are uh, sub-word tokens. But just for simplicity's sake, we stuck to word level tokens. That means each word is a token. So let's say you've got a vocabulary of, in this case, 6,587 different words in your vocabulary. You assign an index to each of them. And then there's a way to actually create uh, embedding vectors for each word. Now, the idea was you're basically trying to say that, okay, let's try and represent each token as a vector of with 512 dimensions. We sort of went through, how we did that, how we do that with Candle, specifically, you know, what this 512, what this 512 number is according to the original paper, and how that's going to be relevant as we go along. We also talked about the standard, what is that? Yeah, the transformer model, which is something like this. Yeah. So we talked about this particular transformer model. We said that your inputs, which is your basic English language, is converted into what is called an input embedding, which are nothing but vector embeddings, as you saw. Then the next thing that I want to talk about, because we're going to go pretty slow and I want to really understand what's going on inside this, uh, you know, this architecture. They call the transformer architecture. So basically, at the heart of it, you've got a bunch of tensors that will flow through this architecture. Your inputs are converted into input embeddings, and then you have something called positional encodings, which are again tensors at the heart of it. Then you perform an operation, in this case, a simple one like an add operation. And then the output of that sort of feeds into what is called the multi-head attention block. And along with that, a copy of that goes to the normalization layer or the add and norm layer. And then you keep flowing. These tensors keep flowing through and stuff keeps happening to them. And finally, you end up with some sort of a prediction problem that you're solving. All right, so that's input. Uh, sorry, was that? Yeah, so we're looking at the encoder part. In the encoder part is the left, everything on the left-hand side that you see is the encoder. Everything on the right-hand side is the decoder part of the transformer architecture. Now, in the encoder, we sort of went through this in the last part. In this part, we'll talk about positional encodings and how the paper sort of walks us through them or how the paper defines them. So, yeah, so input embedding is done. We've seen this. Now let's look at what is a positional encoding. We know that each word has been mapped to a 512 to a vector with 512 dimensions each, right? That's great. So we know that a word is represented as some sequence of or some vector of numbers or rather floats. But we'd also want to capture positional information of those words in a sentence because words have certain words at certain positions mean certain things, right? So where they are in a sentence absolutely is important. It tells us more about what the sentence is trying to convey, and that's exactly what we want to do. We want to sort of incorporate positional information into uh, you know into our process or into our architecture to sort of help us understand a sentence better. So the way this is going to work is it's again not that. Let me sort of, you know, just make this a little smaller. Yeah, so positional encoding, if you take it from the top, you say you've got your original sentence, you get your embedding vector, and then what you do is you also have what is called a positional embedding matrix, which is pretty much another sequence of 512, uh, you know, another vector of 512 dimensions for each word. But the way this thing is calculated is interesting. We'll sort of look at that. This is only computed once and then is reused for every sentence during training and inference. Now, apparently, the original paper says that, yeah, this is only computed once. I guess some other models may not necessarily look at it that way. They may end up recomputing it every time. So that's a different story, but let's just stick with the paper. Uh, so they're only computed once and reused for every sentence during training and inference. So that's great. So your positional encodings for all words, all sentences, etc., are usually computed once, and then you just keep adding this matrix to whatever's coming in as input tokens. That makes sense. Finally, the input to the actual encoder is going to be this plus this, right? So that's kind of what we're looking at. And the way the paper actually works on this is PE, which is positional encoding, is a function of uh, it's actually a sine or a cosine, depending on whether it's an even position or it's an odd position. So if it's an even position, which is 0, 2, and you know 6, etc., you will see that we'll use this particular formula. If it's not, we use this. And I'll show you how this is sort of written in code so that you know how we do this better. But mostly our goal is not to somehow reinvent all of this. This is all old stuff. This is our intention is to sort of understand the candle framework better. So let's focus on that part. Um, and then there's also one more part. Why are we doing this? Well, because if you think about it, sine and cosine are obviously trigonometric functions, and also those functions are effectively repeating patterns, right? A sine goes one way and a cosine goes one way, and it repeats itself over and over again. It's sort of, I wouldn't say cyclical, but it has a pattern to itself. And so if we can inject this sort of pattern into our input, when we train our model, it may just be the case that the model will learn this pattern. And so it's sort of easier to explain this to the model saying, yeah, positions, here's how you learn positions in a sentence, right? So that's kind of why you're using the sine and cosine part. But that's all extra statistical yarn, not important. Let's look at the implementation specifics. So that's pretty much positional encodings. Now let's take a look at how this is implemented. So in my little project called Optimus, cool name, very simple project, you've got a folder under source called embeddings. We just looked at the input embeddings part. Now let's look at the positional embedding. So the way we do this is there's two particular sub crates, you can say, within Candle. Let me actually take you through to the actual GitHub page and search for Candle. That's right there. You will be able to see, I hope this is okay. Sorry. So you will be able to see that, again, well, I've seen a lot of projects go back on this multi-crate, multi-crate project layout structure, going back into like a single repo structure. But anyway, I don't know if Candle's going to go that way, but for now, I guess it's multi-crates. So you've got the Candle edit crate, and then you've got the Candle core crate. There's Candle core, yeah. So Canton 4 has the most basic parts included in there. For example, this is where your tensors are defined. That means what is a tensor in Rust? You know, what can you do with it? All of that stuff is defined over here. I can show that to you. For example, we go in here, you will see that you have a tensor here. And yeah, so it's got all the, the basic stuff, the core stuff that is part of the Candle library is all present here. Tensor is obviously one of them because everything is just tensors in, you know, generative AI or machine learning or whatever you call it. So that's one. The second thing is you also have uh, the sorry the device and the result. We sort of looked at the device. The device is basically talking about, are we talking about CUDA or are we dealing with Metal? Metal is basically the framework that's used by Apple and all of Apple's GPUs for A, graphics, B, GPU computing. So, uh, yeah, that's one. So you've got a bunch of different things that are neatly laid out. I do like this, the way this is being laid out. And then you've also got dropout. Well, dropout is basically speaking uh, when you want to sort of remove uh, stuff from your tensor. I'll tell you why. But when you want to remove stuff, you want to use this. It's basically a float, nothing else. It's just a wrapper around a float, F32 for that matter. Um, so the way positions embedding is implemented, I guess if you just look at the formula, it should be very straightforward. Because if you just look at this, see, we've taken the word, we are basically going to we're going to take the positional information from the vector embeddings, and then we're going to calculate uh, the positional encoding for this. So let's just get started. Let's try and see how that's done here. So what's happening here is sorry, I meant to say you don't create this from the vector embeddings. This is separate. We'll talk about it. So the way this works is sorry, IntelliSense can be irritating sometimes when you're explaining stuff. For example, uh, so you say that, let's just start with a random tensor. I'm going to say that I have a tensor which starts off with 0 and it's as big as the sequence length. Because if you take an English sentence, you've got say 6 words in it. So that's exactly what I'm trying to say. I'm basically trying to get what is called the context length in many ways, but uh, just say the number of words in a sentence. That's what I'm trying to figure out, the position for each of those words in a sentence. And then the denominator over here is going to be this part, which is this whole thing. So we got the position, we got to get the denominator part. Then once we get that, then we'll apply the sign to, the position divided by whatever the denominator is over here. That's exactly what we're trying to do. There's no rocket science over here, right? So we calculate the denominator. We again do the same thing. We calculate a range, and we're sort of stepping through a couple of things, which is, imagine we're just implementing exactly what's written over here. No rocket science here. This should be pretty straightforward. And then what we do is we're going to call unsqueeze. So this is something that I learned, which I did not know. And this is very common if you use it in PyTorch, etc. So it's directly from PyTorch. Unsqueeze is something that that creates a new tensor. So if you basically call the method on the existing tensor, it's going to create a new tensor with the dimension size of 1 inserted at the position that you've supplied. So if I say, unsqueeze whatever this tensor is, that means, as you see over here, I think this is pretty simple. So if I have a tensor which is of shape 2 by 3, that means it's 2 rows and 3 columns. And if I say A unsqueeze 0, and then you compare the dimensions, you're going to get, you won't have a two-dimensional tensor anymore, you'll have a three-dimensional tensor because the first dimension is going to be added to uh, the position that you've mentioned over here. So this is the 0th dimension. I want you to basically expand the the tensor. Yeah, so gotta keep that in mind. Uh, so we do all these operations. This is not important. But then we simply come out and say, okay, so here's the point. This sign is to be applied to this, and this position. Cosine is supposed to be applied to this position, and all the odd positions are there. So we have to take that into account. That's kind of why we start off by saying, okay, uh, give me the first column in, and then go one by one, saying, okay, give me the even columns, give me the odd columns, give me the even columns, give me the odd columns, and keep concatenating each of them until you get to a point where you have your requisite positional embedding tensor. And then finally, what's produced is going to be a little out of sync. So you need to reshape it and transpose it and unsqueeze it. That is when you finally get your positional embedding matrix. And that's how you create a new positional embedding matrix. The easiest way to understand this would be to actually, run it and see. Because if you see here, I think we covered all of this. We've got a pre-trained tokenizer. It's a word level tokenizer. We've also done the encoding for it. We've gotten the IDs for it. We even printed the total vocabulary size. All that is great. And then what we do is we create new input embeddings and we basically call forward on it. We should also technically be able to do, the addition of your positional encoding. Let me see if I have uh, gotten them down here. So yeah, so pretty much I'll have to do this and then just add them up, which I could do, I guess. So sequence length is, what did I use in the previous one? And I'm just trying to figure out which ones to like. Okay, here. 1, 2, 3, 4. Oops. Like I'll have to do a little bit of work in this. Yeah, so if I just go by the paper here, I think I should have them. So if I just go by the paper here and I say 6, and D model is nothing but D model. And he's gonna have dropout. So I'll need to add a dropout differently. So I'll say okay. Let me just minimize this. So I got positional embeddings, and theoretically I'll just need to add them. I'm hoping this will work, but let's just double check this. Let wait a minute. This is going to be more than, so give me 1 minute. Okay. Okay, so this is an 8 by 512, so I'll do the same thing. All right, do an 8 by 512. I got my positional embedding because you remember for each word you're going to have its position. So I'm just taking random stuff. Okay. So this is the output without the positional information added to it. Now, if we were to simply go ahead and add the positional embeddings to this, which would mean that we would do something like let encoder input be equal to embeddings plus be dot forward. Wait. Let me just close the main pieces. Yeah. So I've already done the thing over here. So, oh, why am I doing that? That doesn't make sense, right? Be dot forward, and then I need to pass in embedding. Hey, the problem key, sorry. All right, so I get my tensor. Now I can simply go ahead and print this and uh, right, so that should work. Right. So that's it. It's quite simple. There's not a lot to be thinking about over here. So I'm just going to create my encode input. Let me just run this, see how this works. We already saw that that's the input for just the vector embeddings. If we run this, we should be able to get something that just went bad. Uh, okay. Hey, I already did any test. Mm. And here's how you can exclude this from being trained. Because you remember we talked about positional embeddings only being computed once, and then they're reused for training and inference over and over again. This is how you'd sort of do that. Uh, what is important is Mhm. Okay, why am I getting this error? Looks like my shape is not correct. Length one. Hmm, that's interesting. Okay, let's try and do this. Look at this. Let's try and do this. Bearings. Wait. Oh, just for the hell of it, let me just try this. Want to see what's printing. Something's wrong. Okay, looks like I've got to take this call, but yeah, so technically I think you should be able to get this. We just do the addition and then we should be able to incorporate position information into our vector embeddings so that that becomes our encoder input. I'll sort of add, you can ping me on, in the comment section. I'm going to fix this. I'm running out of time because I head into something else as well. But I hope that makes sense. So just to recap again, we've got positional encoding is basically you take, uh, you create your positional encoding matrix for, that means you've got another 512 dimensional vector for each word. Now that's only encoding positional information. You take that and then you simply add it to the vector embeddings for each word. And then finally you get your, you know, uh, encoder input. That is basically this part. So you add this and this. So whatever comes out of here is what is your encoder's input. So this is actually the encoder and this is the input stage. All right. Yeah. So I hope that makes sense. Yes, I know that there's one part I was not able to get this, I was not able to debug this right away on this screen. Yeah, I'll try and do that in the next stream, or I'll just post a link to, what went wrong. Yeah. Thank you. Have a good day.